Hello, everyone, and welcome to our second workshop. So I'll spend about 30 minutes going quickly over the workshop agenda, and I'll make a request for your post-workshop input. I'll tell you a little bit more, basically remind you from the last workshop about the SCOC process, remind you of timeline for arriving to phase 2 recommendation, and then we'll go back to phase 1 recommendations, which is the main topic of this workshop. And we'll go over those 7 questions where we made specific recommendations. If you registered for the meeting, you signed code of conduct. There were a few people who didn't register, but we sent them Zoom link anyway, and then we reopened registration. So even if you did not sign code of conduct, we still expect you to follow our code of conduct. And again, reminder that all sessions will be recorded. So your image or your voice may appear in those recordings that we will make publicly accessible. We will have 2 days, each day 4 hours, and break is at the same time. These are Pacific times. So we'll have 15 minutes break between 2 sessions on each day. Today, in first session, after this talk, we'll have Peter talk about new sets of simulations, and then Lynne will talk about metrics implemented in metrics analysis framework. In particular, she'll describe which metrics are being regularly run with those new simulations that Peter will introduce. And in session 2, we'll have a bit more detailed analysis of those metrics, comparing what changed between 2 baselines. And then we'll talk about what we learned using these metrics in V2 simulations. And then we'll end the day today with your feedback, with science collaborations feedback, which will be organized by science collaboration, by 7 science collaborations. The 8th one, the one on informatics, I forget exact name, decided that they did not have anything specific to contribute here in the context of Cadence. So we'll have about an hour and a half for 7 collaborations to present their feedback. Tomorrow, we'll talk more about the code, the simulations, the refactored code base, which is now much easier to install, much easier to use. And then Eric Nielsen and Lynne and Peter will lead a tutorial session tomorrow. And we'll end the workshop with community feedback, with community organized session that will be additional feedback. And we will have 4 presentations on deep drilling fields. Then there are 3 time domain collaborations that we'll present, that's organized by Angelika. Then we'll talk about metrics that we'd like to add to our metric set, especially in the context of galactic science. And then we'll end up with discussion of targets of opportunity. We'll also have Bob Blum, operations director, participate and provide input on how exactly we plan to treat targets of opportunity once we enter operations. So as you know, Survey Cadence Optimization Committee always welcomes your input. We do understand that there are only 11 of us, that we don't cover all the expertise in the area of astronomy and astrophysics. We always welcome your input. And so we know that this agenda is very packed today and tomorrow. And we would like to ensure that if you have something specific that you want to bring back to the SOC as your feedback, that you can do that. So we invite you to write down your reflections, comments, or any other input and send it to me by email. And then I will circulate it to SCOC communication pages and emails, and we will then have a meeting where we will discuss all such feedback that we will collect after this workshop. So please feel free to send your input if you don't get a chance to present it at the workshop. Let me spend a few slides just reminding you about SCOC. You already know that from last workshop if you participated. So the basic purpose of this committee is to make our survey, LSST, that data set, as good as it can be given Rubin Observatory, given observing conditions, and given all of us and tools that we will be using. By design, SCOC is made of experts. It's transparent in its deliberations. It's diverse, it's inclusive. And there is much more information about SCOC at our webpage, public webpage, and also there are many useful links to various documents from our previous discussions at that link at the bottom of the page. By the way, all the presentations are all but one are already linked at the web pages, so you can download all these slides later if you want to get one of these links. SCOC is charged with 4 tasks. The one we are discussing at this workshop is specific recommendations for the Cadence choices for the main survey, for the 10-year survey that includes what we call main or wide fast deep survey plus other mini surveys and micro surveys. We also expect SCOC to freely communicate our discussions and recommendations to our stakeholder community. Once we are done by the end of next calendar year with phase 2 recommendation, basically, once we define baseline strategy with which we will start the survey, start operations in hopefully 2024, then we will spend, SCOC will spend 2023 to talk about how the baseline could be modified during the year 1 to enhance the so-called early science, where early science is defined as all the science we will produce prior to data release 1. And then during operations, SCOC will support the project team that will track survey progress, and we will use SCOC to make formal recommendations if we will need to update survey strategy. Here is the current membership. You can also find it on our web pages. I put it here because the end of each line tells you to which science collaboration these members are liaisons for. So if you are in a science collaboration, there is a member of SCOC who you can contact and then express your concerns, feedback, etc. So quickly going through our timeline. So we released draft phase 1 recommendation report in August at PCW. We are having this workshop now to receive your feedback. And by mid-December, we plan to incorporate all the feedback that we receive from you at this workshop. And that week after the workshop, then we'll work for a few weeks on finalizing this report, and we will formally deliver it to the operations director, Bob Blum. And then early next year, simulations that are described in that report will be delivered. A huge fraction of those simulations are already available, and Lynne and Peter and Eric will be talking about them. And then sometime next summer, we will have another workshop where we will come back with the analysis, with analysis results for that new set of simulations. And then we will use that to fine-tune baseline strategy. We call it now V2, and then we will produce V3. We'll decide what V3 will be around summer of the next year. And then sometime during fall, we will produce simulation and all the math metrics for that final strategy. And that final strategy then will be incorporated in our observatory control system. It will be ready to start the survey. And we will deliver that report to operations director by the end of next calendar year. And note that that report, that final baseline, will be delivered more than a year in advance of operations. One reason is that the project team will be busy during 2023 with commissioning. And the other reason is that SCOC will be spending 2023 trying to think about modifications to baseline V3 that will further enhance early science. And we are hopeful that we will start operations in early 2024. Our early completion date for construction is January 24, and we carry schedule reserve of 6 months, so late finish would be June of 24. Currently, operations team is using April 1, which is mean value of those two, as start of operations for their proposal to agencies, funding agencies. So date to remember is early 24 for the start of operations. I just want to remind you there will be data previews, and in particular, data preview 1 will deliver real LSST data from commissioning obtained with commissioning camera, 1 raft, and then data preview 2 will deliver in 2024 data obtained with the main camera, about 2 months worth of hopefully science quality data. And then first data release that will be based on first 6 months of data will be sometime in 2025. So we are getting very close to getting real data on our computers. So if you want to have a preview of our thinking about early science, I put link to RTN 11 that Lynne, Guy, and collaborators developed. And again, 2023 will be reserved for early science modifications. Of course, we need to better understand system performance in order to do this final step of optimization of the survey cadence. So let me now go to quick summary of phase 1 report. Here is the link for it, and details are there. I'm just going to do very high level summary of those 7 questions. I already told you about this, so let me move on. Important note about metrics. When we received cadence notes, there were many ideas that were not fully based on quantitative metrics. And that's fine, as long as we can understand what was proposed and SCOC thought that was good science to be explored, we implemented in simulations. However, to do quantitative analysis and to do quantitative optimization of final baseline, we need metrics. We need to know how your science responds to those changes in simulated cadences. So we really, now is the time to deliver whatever is on your mind. There is no more time to wait. If we don't incorporate them into math by the end of this year, they will not be run on that new set of simulations that Peter will talk about. And they will not be then used quantitatively in SCOC's phase 2 deliberations. So this is important. And in particular, it's important for galactic science for definition of exact footprint, etc., for galactic science. So I cannot overemphasize this. We need these metrics. So the first report, phase 1 report, was based on 39 cadence notes that you guys submitted, science collaborations submitted. We are very thankful to you for these notes. That's what we use as quantitative input. Thank you, thank you, thank you for that. It's really important to have this input to SCOC's deliberations. If you want to see what other people submitted, if you submitted one note, you can go to this link. All of them are available there. And given these 39 cadence notes, here is the process that we followed when we synthesized your input and then distilled that input into specific recommendations for those 7 questions that we posed to you. So we had process that is by and large modeled after NSF proposal review panels. If you ever went to, before COVID, to DC to sit on those reviews, you met that process. It's basically a large set of proposals that you need to process, and then you have 2 or 3 people focus on particular proposal. Here was slightly different. Instead of focusing on particular Cadence nodes, we had those 7 questions. So we split SCOC members into small teams of 3 people dedicated to each of the 7 questions. And then those people read discussion of that particular question in all 39 Cadence nodes. And then they produced reports, summary reports that they presented to the rest of SCOC. And then we had a series of telecons where we went question by question. So we listened to the summary reports, we had discussion, and then we agreed on recommendation. And we always reached consensus. We never voted. Everybody agreed with given recommendation. In some cases, it was easy to arrive to that point. In some cases, we had much more discussion, but for all 7 questions, we arrived to SCOC consensus. Again, thank you for sending these inputs, these Cadence notes, because that was crucial part of the entire process. So let me now go quickly through those recommendations. I will not cover the entire report. The first part of the report provides background and detailed information about the process. The last part discusses phase 2 survey simulations. You will learn more about them from Lynne and Peter after this talk. I will only go quickly through these 7 specific recommendations. So the first question talked about footprint definition and whether we would want to increase it if we could by about 10%. Various estimates of system performance, and those estimates are based on some measured properties of hardware components that we have. In some cases, they are based on simulations, sometimes informed by past observations, for example, weather simulations. In some cases, we had to just assume things. So this is not the final word. We have to get through commissioning to be able to claim that we understand system performance at 10% level. But at this point, this is our best guess. We think there may be a possibility that we could squeeze out 10% more science in terms of integrated at and do than originally designed. And if this is true, then we ask what to do with that. And so one possibility is to increase footprint. And it turned out that in your responses in those 39 Cadence notes, the strongest message was, it is not so important that we change footprint by 10% or so. Much more important is where exactly do you place it. And on the left, you can see the original design of the footprint boundaries, which was driven basically by stellar count distribution in the Milky Way. And on the right, you can see the new baseline V2, where those boundaries are defined not by essentially straight line in galactic coordinates, but instead they are defined by placing a limit on the maximum interstellar dust extinction for the extragalactic survey. So the green part goes as close as possible to the galactic plane, but keeping away from dust extinction higher than, I forget now, 0.2 or 0.3 magnitudes. Lynne and Peter can later tell you which number they adopted in the end. So that was the change of footprint that we'll discuss in much more detail in the remainder of this workshop. And then now we are still in optimization phase, so we don't have final answers, but this diagram, Lynne shows that if you take our design value of 825 visits, that's blue line, and you take our 18,000 square degree design value for survey area, that we could accomplish this with about 80% of time, total simulated time in the simulation. Now, SRD assumed we would need 90% of time. And so if these simulations are correct, and again, don't start jumping up and down and saying we got 10% more, because this is just an estimate. We have to wait for the end of commissioning to be able to say this diagram is trustworthy. For now, it's just our estimate, but if it is true, it will be great news, and then we would have 10% extra. So the next question was about how to use the time. And so one possibility is just to add more deep drilling fields, for example. The other possibility is to add microsurveys. And indeed, we had 9 proposals for those so-called microsurveys. The nomenclature is not exact, but roughly speaking, mini survey would be something that takes of the order 10% of the total time. Microsurvey will be something that takes of the order 1% of total time, just to put it in the right ballpark, but these are not legalistic definitions. So we will attempt to simulate all of these, and you'll hear more about details later from Peter and Lynne. Then we had discussion of 2 snaps versus 1 snap. As a reminder, the original reason for having 2 snaps was to be effective at finding cosmic rays. And the other reason is to measure very fast transients to detect changes in flux on timescales of sub-minute, of few tenths of seconds. It turns out that cosmic rays in our fixed CCDs will not look like, for example, they looked in SDSS. That's what guided our thinking. They will not be 1 or 2 pixels basically sharper than PSF. In thick devices, they look like little worms, and it's much easier to find them, to recognize them from morphology. So it seems that we will not need 2 snaps for that purpose. And if you do 2 snaps, then you lose efficiency because of 2 readouts, and you pick up noise. And so there is strong desire to go to 1 snap, but at this time we thought we shouldn't do it, because if we go to 1 snap now, because of various effects with software, etc., it might be irreversible change. It would be hard later to undo it. So at this time, we only decided to switch to 1 snap in U-band visits. And the reason why U-band is that sky is very dark in U-band. So the impact of readout noise is much more significant in U-band. And so by switching to 1 snap instead of 2 snaps, you actually go significantly deeper than with 2 snaps. That was the driving thing. And also we will try to re-optimize the exposure time in U-band, because a lot of astrophysics is revealed by accurate U-band observations, both in stellar and extragalactic astronomy. How am I doing with time? I have 5 minutes left, okay? So then we also reconsidered the per band observing time allocations. If you read SRD, you may recall that we call it there just an illustration that was driven by photometric redshift simulations for galaxies. That's how we assigned those allocations. And it looks like we guessed well, so nobody had a strong argument for changing them. Then there was discussion, important discussion of whether we should use the same filters or different filters when we have pairs of visits on a given night. And there are arguments for both, for same filters and for different filters. And SCOC recommended, for various reasons, that pairs of visits be obtained with different filters. And now we are trying to optimize what filters, what exact filters to use. Do you want to go GR or GI, or how do you want to combine the two? Is still open to optimization. Then we also talked about rolling cadence in cadence notes and in SCOC deliberations. We have some rolling cadence simulations, but our team, Peter and Lynne, believe that they can be further improved. So this is not the final deal. And basically, recommendation is to continue to explore and improve rolling cadence scenario. And there is a Tiger team organized by Lynne and Peter that will include a number of people from science collaborations who are interested in rolling cadence and submitted those cadence notes. So we will produce another family of rolling cadence simulations. And also they will be discussed in more details during this workshop. And finally, we also discussed dithering patterns, and there are no strong arguments for changing what we have now. Of course, this is again based on our assumed performance. We don't know exactly where, for example, ghosts will be in field of view, what will be their impact, etc. There are certain science programs like weak lensing that would be very sensitive to such details. So for now, we will not change anything, but once we have commissioning data, then we will revisit issue of dithering again. So to summarize, this is my last slide. Top recommendations were to redefine footprint using interstellar dust extinction limits that was driven by extragalactic astronomy. So this green part will speak to extragalactic astronomy, and this purple part is galactic plane plus so-called north ecliptic spur on your top left, designed to deliver more solar system science. And then we also have south celestial pole at the bottom. We decided to go to one snap for U-band visits. We decided to use different filters in nightly pairs of visits and to continue to explore rolling cadence scenarios. So I will stop sharing here and I will take your questions. Oh, I see there is something in chat. Okay, so Lynn, more information. Okay, so it is reddening that is defined as 0.2. So roughly speaking, we have about 0.6 magnitude in V band, which is very similar to the R band. So about 0.6 magnitude R band extinction is the limit that defines extragalactic footprint. Are there more questions for me? If there are no questions, I would ask Peter to start sharing his slides while you may be thinking. Oh, I see hand from Meg. Meg, please go ahead.
I'm gonna say I'm wearing the Solar System Science collaboration hat on this one. There are things that are particularly that in Cadence notes, like a solar system deep drilling field, which effectively is a, I don't even know if it'd be a micro survey, but a nano survey of effectively 40 hours. Obviously, there's no point in simulating that because it's equivalent to a night of bad weather over the whole survey. But that's not something obviously that the SCOC wants to consider at all at this point because you're doing big broad strokes. So can you give a little information of how things like that are going to be settled? Is that something that's going to be like director's discretionary time that might pop up? There's 40 hours available in a semester or a year to do something that's we think of along the way that's small, or these things that have already been thought of could be adjudicated and decided whether they will get time or be the schedule will be able to implement that.
Right.
Because right now you're doing all these big things and just for these very small amounts of time, is there a rough idea of what will happen? Or what way forward, or should we be continuing to remind the SCOC about these things for the next year and a half or 2 years?
Right, this is a very good question. So this is 0.1%, roughly speaking, of the total time. So at this point, there is no reason why we would simulate something like this, but eventually there will be director's discretionary time. We had discussions on that. I don't think it's decided what fraction of time would be director's discretionary time, but various committees were throwing around numbers like 1 to 2%. So something very similar to targets of opportunity observations where the exact rules are not settled yet either, but we will learn more about current thinking from Bob Blum, I believe, tomorrow. So similarly, in this context, there will be some process where you could say, hey, with 0.1% of LSST, we can deliver this fantastic science, and then you will describe just like you would to time allocation committee. And then if there are more such proposals, then someone somehow would have to down select it. At this time, it sounds like SCOC will be a committee that will be present in operations, and it's well equipped to make such a decision. So at some point it will happen. In this particular case, I don't see why it should happen first year, and we will be busy with so many things first year, including getting to DR1. So after we push DR1 out, after we demonstrate that we are alive and well and science is being produced, and we can actually do steady state observations and reach our target efficiency of the order 1,000 visits per night, etc., then it will be good point in time to start considering in gory detail all these other proposals and start adding here and there such 0.1, 0.2% proposals. And maybe if we really have 10% better performance than we originally envisioned, now we are talking about being able to accommodate 100 such proposals. So who knows what kind of great science we will get on top of everything, because people will be thinking about what to do and find ideas that we never thought of before.
Thanks. So for now, your recommendation is that's not something the SCOC wants to hear about. So it's in the back of your mind, you're aware of them, but you'll come to, rather, we'll hear from you when you're ready for those kind of.
Right, there will be a call, formal call, but people can submit their ideas. I mean, I'd rather have, we can easily add them to SCOC Confluence page, for example. If someone has great idea, let's put it there so people will change. Different people may be optimizing this later. Different people may be SCOC members. We don't want great ideas to get lost. Thank you, Meg. I don't see any other questions, so I propose we continue with Peter.
Okay. Good morning, everybody. I'm going to talk about our new set of simulations that we've just released. So I figured I'd give a very lightning fast reminder of how the scheduler works for Rubin. So at the top tier, we start up the telescope and it says, are there any deep drilling fields that need to be done? If there aren't any deep drilling field sequences that need to be done, it falls down to the next tier where it says if it's not twilight and there's enough time, observe a large contiguous blob on the sky. And we do this in pairs, so either U plus G, U plus R, and so on. And it'll observe a large blob and then switch filters and repeat. And so that second observation is separated by about 33 minutes. And this sky area is selected using kind of a linear combination of 5 sigma limiting depth, survey footprint progress, and slew time. And so this is the Markov decision process that goes through to decide on that contiguous region. If it's twilight or we don't have enough time to do these large blobs, we go to a smaller blob and redder filters, and then these will be paired with just 15 minutes instead of 33. And if there's not enough time to do a 15-minute pair, it falls down to a greedy algorithm and just picks an R, I, Z, or Y observation singly to do. And so all 3 of these lower tiers are using the Markov decision process. We have a kinematic model for the telescope with historic weather, seeing conditions, etc. So we can simulate 10 years of observations and generate a log of about 2 million observations altogether. Here is the new baseline footprint that Zeljko showed. Just to label everything so everyone knows what's going on, this top tier is the North Ecliptic Spur. The large green region is kind of the low extinction 17,000 square degree area, often referred to as wide, fast, deep. We've got the dusty plain where we observe a little bit less. We've added the bulge here. So this is a high extinction region, but we've added it. So and we can kind of consider it as part of the wide, fast, deep because it will meet the science requirement document limits. We have the South Celestial Pole where we don't observe too much. We've got some little blobs down here that are the LMC and SMC. And you can kind of see, it's hard to see on this stretch, but you can see we've got 5 different deep drilling fields throughout there. And this one is our newest addition. It's a double field that is the Euclid deep drilling field. Okay, so I'll go over what's new in 2.0 and what will be coming in 2.1. So first off, we've got our changes to the footprint. We decreased the dusty plane, we covered the bulge, we added the LMC and SMC, we increased our pair timing from 22 minutes to 33 minutes. When we were looking at solar system object detection, it seemed like going to 33 was fine, and that increases our efficiency slightly, so we did that. Another big change between our old baseline and our new one is our new baseline includes rolling cadence. So here I'm showing years 2.5 to 3.5. Before, we would just cover the footprint uniformly. Now we have some concentrated bands that we do more observations on, and the next year, these low density bands will be increased so that after 10 years, they look the same, but we have some high cadence and low cadence regions each year. So we're getting up to 140 visits per season instead of the usual 80. All right, and this is a lot of progress here. I just made my favorite radar plot showing the very old Minion simulation that some people might remember. Our baseline 1.x and our baseline 2.0. Basically, Minion took pairs in the same filter. It would basically just do one filter per night. It rarely switched filters during the night, so it was terrible for supernova detection. So we've really boosted type 1a supernovae by going to mixed pairs, and then by doing rolling, that gives us a big boost to baseline 2.0. By covering the bulge, we get a huge burst in faster microlensing events, and then everything else is pretty much the same. The one thing we lose on is faint NEO objects. By going to mixed filter pairs, we lose a little bit of faint near Earth objects, but other than that, it seems to be a boost across the board. Okay, so our new simulation families that we've run. The first one is just what we're calling retro. It's like our 1.x version baselines. This is just so you can compare and double check and make sure our change in footprint didn't damage any science cases. And we have one that's purely classic and one that's like our new baseline, so it includes rolling and the longer pairs, but with the old footprint. So, and right now we really don't see any case for sticking with the old footprint, but you can double check. We have a simulation where we went with bluer filters. I think there were two simulations in this family where, in the baseline, we have about 70 G-band visits over 10 years. And then in one of these, we pumped it up to 94. We don't have a lot of metrics that constrain our filter distribution. I know there's, PhotoZ metrics in the works that we need to get merged in. But it would be good if we had some science constraining these filter distributions, and if one of these is better than the other. All right, long U, Zeljko mentioned that we switched from 2 by 15 second snaps to 1 by 30, and we also tested going to longer U-band exposures. So this is using 50-second U-band exposures, and one simulation where we keep the number of exposures the same, and one where we keep the total exposure time the same. And so you can see the color bars here are different. Here we've got only 40 U-band observations, and up here we're still at 60. So tidal disruption event folks should weigh in on this. I know their metric is very sensitive to U-band, and again, PhotoZ would be good to know, which of these is preferred, because obviously putting more time into U does hurt some science cases. Okay, long gaps. There was several white papers noticed that in our previous baseline and our current baseline, we really don't sample time gaps of order kind of 4 to 7 hours. We were taking pairs at 33 minutes, but here I've got a histogram of kind of all the gaps in observations, and there's a real trough in that 4 to 7 hour range that we just don't sample. So there could be interesting events going on in that time scale that we just don't see. So we ran a whole lot of simulations where we intentionally start the survey. Here I'm showing the distribution of alt as in the baseline, and then in here. So we'll start each night in the east for an hour or so, and then wait for those points in the sky to rise and observe them again later. So we get a boost in this kind of 4 to 7 hour time window. And that, because we're on a spinning Earth, we have to do this. We have to push to high air mass if we want to sample these time scales. And so we were successful, we're sampling them, but we need some science metrics to say what new science can we do now? We really don't have anything. We have lots of science metrics that say, wow, it's really bad that we're going at higher air mass now and losing signal. So we need to take the next step to say what's the science that we can enable with this, and how much time should we spend doing it. All right, Presto and Presto Color. These are simulations, again, driven by the white papers, where this is where there's a big tension between transient detection versus transient classification. In our baseline survey, we will tend to observe a point on the sky twice in the night, so you get a color. Here, there's, if we want to actually classify transient events, it would help to also have a slope to get a third observation within the night. So these families are really pressing to get that third observation. And here's kind of looking at 1 year where we're color coding what filter is in the telescope at a given time. And here in Presto, and so you can see we've got red stripes here that's driven by the moon. When the moon's up, we go to the Y and Z filters. And so here in the Presto, we're doing a lot of, we've given lots and lots of time to Presto, where we observe a pair early, wait a while, and then get a third observation kind of, 1.5 to 4 hours later. And we do it all the time. So this should be great for transient classification. We don't have a lot of metrics to say how well can we classify transient objects, especially on these shorter timescales. So we really need metrics to say, now that we've done these Prestos, are they working? Are we going to be able to classify many more transients? And we've run simulations of these where we do Presto all the time or on only half the nights to kind of lower the impact, because when we do it all the time, there's actually not enough time left for wideband observations to get to where they need to be. Okay. And rolling, we've got lots and lots of different rolling experiments. We've got our classic no rolling. We've done some extreme rolling cadences where we actually divide the wide, fast, deep area up into 6 bands. So we're getting, close to 400 observations in a single year. So just a very high cadence, nearly nightly observing on a small section of the sky. And here's an example of our baseline half the sky rolling in wide, fast, deep, and dividing the bulge into 6 bands. So you can, depending on what part of the sky we can mix and match and do different rolling strategies in different parts of the sky. So we don't need to worry about if extragalactic folks want one kind of rolling and Milky Way bulge folks want another, we can do that. What else do we need to say about rolling? Oh yes, and all of these strategies look the same after 10 years. There's very little impact on static science because we eventually even everything out. One thing we'll talk about later is we almost always start the survey going uniform so that we can get good baselines for proper motions. We did one simulation where we push it earlier, and that does have a slight impact on our proper motions, and we are right on the edge of what we want for the science requirements document on proper motions. So that's a tension we'll get to. Another tension with the rolling cadence, because we're doing part of the sky in depth and another part not as deep, it means the annual data releases will not be uniform. So here's an example of kind of our extragalactic depth. At year 3, we've got these bands because we're in the middle of rolling. Year 6, there's still some slight bands, but it gets better. So we need a way to quantify how bad is this? Do we need to mitigate how we're going to have uneven data releases if we're rolling? It evens out in the end, so that will be an interesting debate. Okay, varying the galactic plane. So we, it was kind of just back of the envelope, cutting down, deciding how much to cut down this dusty region. So we have a whole string of observations going from very few visits in the galactic plane all the way up to giving it the same number as wide, fast, deep. So this will be great. People can show their science cases for why we need more or less visits in the galactic plane. Similarly, for the North Ecliptic Spur, we went from very, very few visits in the North Ecliptic Spur to cranking it up to nearly the same number of visits as wide, fast, deep. Luckily, we have lots of solar system metrics already. And I think they're actually running right now on the cluster at UW. So we'll have those soon. I was surprised. I didn't see a lot of strong trends even when I turned it down very low. It seemed like we still recovered a very large fraction of the solar system objects like the baseline. So I would encourage the solar system science collaboration to look into this and look in detail, because I'm not a solar system expert, but they looked similar to me. So we need to know the in-depth science cases for this family especially. All right, microsurveys. There was a huge list of microsurveys. Here I'm showing my favorite because it was the easiest one to implement. It was adding the Virgo cluster to the wide fast deep area. And so this little knob here is the Virgo cluster. So I think we should definitely adopt this one because it was super easy to code and has virtually zero impact on the rest of the survey. The other microsurveys were more complicated and have different impacts. Here's just kind of the massive list of them. Target of opportunity for gravitational waves. This is nice because often a gravitational wave alert will happen in the wide fast deep region, and so it's effectively free. It doesn't cost any additional time. We can use those visits as part of the wide fast deep. There was a proposal to look at local galaxies, several proposals to take short exposures across the sky, adding a northern stripe so that we have image differencing templates for anything that could appear. We looked at the Roman telescope bulge deep drilling field. We looked at the Carina region. We did the Small Magellanic Cloud in movie mode, kind of just observing it all night long. We tried using twilight time for a near Earth object search. There's the Virgo cluster. And I tried using variable exposure times, which seems like it didn't work. It should have worked, but it didn't seem to have a big impact, where we, rather than using 30 seconds for every visit, scale up or down depending on what the observing conditions are like. So a lot of these look great, but we do risk death by 1,000 cuts if we just implement everyone's great little idea. Then we will eventually lose time on the main part of the survey. Okay, deep drilling fields. So we only did 2 simple DDF runs where we gave more or less time to the deep drilling fields. The baseline is 5%, and so I think we went down to 3% or 8% of the total time to deep drilling fields. The SCOC asked for more, and we have Cadence notes and white papers with good ideas. We just ran out of time. So this will be one of the first things we get to in 2.1 is more sophisticated deep drilling field experiments. And we have some good metrics for measuring DDF performance. Definitely need some for static science, and always welcome more. And here's kind of a preview of some slides that I'll also show during the DDF session later. But what we're looking to do for the deep drilling fields, right now they're very crude. It just says, can I observe? Have I hit my observing limit? Yes or no. Here, what I've done is I've pre-computed the 5 sigma limiting depth for a single deep drilling field across the entire survey. And so here's 1 year. And you can see there's a large gap here when it's out of season, it's near the sun. You can see 12 smaller gaps, which are caused by the moon. And then when you zoom in, you can see lots of little gaps where it's just the daily motion of it rising and setting. So we've got the Earth, the moon, and the sun getting in the way of the deep drilling field. And then we can use a mixed integer programming optimizer to place the observations. And so the black dots are where the optimizer has said, okay, here's the best times to observe this field. So we've got this as a proof of concept. We're going to scale it up to all 5 deep drilling fields and try running it that way. And the way it's working is I put in what I desire my cumulative number of observations to be on the deep drilling field, and it does a chi-squared minimization to match that under the constraints that it has to have some altitude limit, some depth limit. It can't be observed during downtime and so on. And you can see the match is really good. It does a great job laying out when the deep drilling fields should be observed. And the point is, this was just my initial curve. We can modify this. So if we want to extend the observing season, we can change the season length. If you want to change the cadence, that's just the slope of this line. And so we can have multiple slopes as it goes up if we want to do what's been called the accordion kind of cadence, if we need extended seasons. We can do rolling. We can have a very low cadence season on a deep drilling field and then much higher the next season. So this formalism should let us do all the deep drilling field experiments that people have proposed and wanted to do in the past. You can also notice that for this deep drilling field, when we turned on the survey, it just started observing it. maybe we don't want to do a half season of DDFs and just wait and do higher cadence when we can do full seasons. Okay, so there are 127 new simulations. The metrics are up on the web if anybody wants to look at them. Looking ahead to kind of the 2.1, hopefully we'll be able to incorporate suggestions that and lessons learned from this round. So, do we want to increase the U-band exposure time? How do we want to resolve this detection versus classification? Do we want to start doing some presto observing as part of the baseline? The north ecliptic spur strength, the dusty plane strength. Do we want to change our rolling away from the baseline? And then 2.1 will have lots of new deep drilling field experiments. However, we do have variations on the DDF now. So if you are interested in DDF science, please start writing those metrics now. Any more micro surveys, any more footprint fiddles that we want to do, and things like that. Okay, so that's my thing. I see the chat's been blowing up, so I can take questions.
Thank you, Peter. There were many comments in chat. If people want to tell them to everyone here, then raise your hand. Otherwise, we'll leave them there and we'll ask new questions of Peter. Does anyone have a question? I don't see anyone.
There were a lot of discussion of the pros and cons of higher mass observations. And I think one of the things that's nice is that a lot of those, a lot of the specific concerns are things that we have metrics for. So, so we can evaluate the cost. I think where we don't have a lot of metrics is where the benefit is in terms of classifying variable and transient objects. And I get that that's a really wide space, so it's hard to come up with a metric, but I think that that's something that where we need to understand what we're gaining.
Thank you, Lynn. I see Federica started collecting pros and cons of high air mass observations. That's excellent. If there are no questions for Peter, then I think we can continue with Lynn. Those who didn't notice, we now have Slack channel 2. So chat on Zoom will be saved, but nevertheless, if we have more discussion, let's move it to Slack channel, which is called SCOC-workshop 2.
Zeljko, there is a question on the chat right now that came after you moved on from questions on the chat.
John would like to hear the project address Dave Monet's comments about the geobelt. There are lots of satellites on the sky, and I think the pain to us is likely to be dominated by LEO satellites, those from Elon Musk and company. It seems that there may be as many as 100,000 those satellites by the time, by midpoint of the survey, by the end of 2030. So I think we'll have to have lots of tools for treating those problems, those streaks, and they are probably going to be okay to treat geobelters too. That's long answer. Short answer is at this moment, we are not doing anything about them. We are not modeling them. I'm talking now about geobelt. We are not modeling them. And there are some other complications with geobelt satellites that we are still waiting on the proper language for public consumption from the agencies. So I will not go further into that discussion. But yes, I agree with you that we could have problems. And at this time, we don't have any program that is working on producing anything beyond what we plan for LEO. And for LEO, data management team has already produced tools to mask them, to find using modified half transform, you find streaks in your image and then you mask them. And with that approach, we believe that the impact of LEO satellites would be at the level of few % of pixels would be lost to that masking. Whether one can do better by actually fitting those trails, whether masking would produce any systematic residual effects that could affect precise cosmology, for example. We don't know yet precisely, but we are thinking about how to do some simulations. We are moving in that direction. So I hope that makes you happy, John. Sorry, I can't be more specific, but we are aware of these issues. So I propose we continue with Lynne. We are back on our original schedule. It's 10 o'clock. Lynne, it's yours.
All right, thanks. I'm going to talk about math metrics. And can you see my, oh, there we go. Slides are all working great, right?
Yes.
Okay. So my talk is rather dense because we have a lot of metrics we're running, and the idea was to sort of go through all of them to let people know what we're running. So there's a lot of metrics to go through. I'll go through them relatively quickly. But first of all, I wanted to note that you can find a list of all of the metrics that are available in RubinSim on our documentation page at rubinsim.lsst.io. And it's a little bit hidden. We need to improve that with the documentation, but there's a list of all the metrics there, and it's at this link here. This can be helpful for finding more information on a specific metric, but this is all of the metrics that are in math. We don't run all of these. Some of them we don't run because they're not obviously useful. We created them at some point in time, but running the FFT metric, for example, to calculate the FFT of visit times isn't obviously useful for people to have for general use. Some may be redundant with other metrics. So in that case, we like to run just one so that it's a little easier to run and easier to interpret. Some we don't actually know how to configure to produce meaningful information. So for example, there are metrics that count up the number of stars at a particular distance, but if we don't know what distances are useful to evaluate for people, then that we can't run that metric because we don't know how to configure it. So to see what we're currently actually running on all of the simulations, the easiest way to do that is to look at the metric outputs that we have online. The link is here. It's astro-lsst-01 at astrowashington.edu. And we have multiple ports where we host metric outputs. So just note which ones you're looking at. 8080 is where we currently have the B2.0 simulations. Knowing how a metric is run is important. If we don't know how to configure it, so we don't run it, obviously the configuration is important, and the configuration changes the output and meaning. So the configuration details are generally captured in the metric output names. But if you want to know the exact details, the place to go and look, you can ask us, but basically we have this kind of configured metric bundles essentially that are in math batches. So the exact details of how we ran something is available there. Okay, so what metrics are we running? If you go to astro-lsst-01 and you look at the metrics we have up on port 8080, you can see that the same simulation name is repeated a couple of times with different math comments. The math comment tells you which metric group or batch was run on the simulation. So we have a series of these. The glance group is a small group of metrics which we can run fast and use to check to see if the simulation had anything go really obviously wrong. The metadata group is a large group of metrics. It just catalogs basic things about the visits. The SSO group are metrics for solar system objects. These are fairly intensive to run and use a slightly different process, so we just end up saving them separately from the rest of these science metrics, but they are science metrics. The science metrics are a growing group of metrics aimed at high-level evaluation of the simulation. Okay, so now I'll talk a little bit more about each of these groups of metrics. So the glance one, I'll go through briefly. Again, most of the glance metrics are aimed at detecting problems with the simulation. So there's a couple of outputs, which are maybe not like super pretty, but they are very useful for the survey strategy team. Things that from this glance group that might be useful for other people. In general, the hourglass plots show when filters are used. So if you have if you look at this plot up here on the upper right, you can see the night, you go increasing in night from left to right and the hour within the night up and down, and the color coding just tells you which filter is in use. So you can see here, this is 1 year. You can see the variation in the length of the night. You can see this is the phase of the moon, and you can see which filter was in use. And this would be like our shutdown period. And this is another maintenance period. And then there's other like this general downtime. So you can see the filters that are being used. Oops, sorry. And the other thing that's actually might be really useful from the glance metric is the roll check. And these show you just snapshots of a few years of the cadence, and they can help you visualize what the rolling cadence is doing. So here we have from the baseline, this is year 2.5 and 3.5, and what visits were obtained in the year previous to that 2.5 period. And you can see that in this upper plot here, you can see these two stripes. So this is our 2 region, 4 stripes, rolling cadence in the dust-free, wide, fast, deep. And so you see this was 1 year, these pointings were the next year, and this is what's, this is just like gives you a little insight into the rolling cadence. So the next group is the metadata metrics. These are maybe not as useful as they used to be, but there are some interesting things there, especially if you're looking for just general characterization of visits. So mostly these are just characterizing the physical properties of the simulation. So we do things like the air mass, the normalized air mass, which is what was the air mass of a particular visit divided by the best air mass that pointing could have had. Things like the single visit depth, the co-added depth, saturation magnitudes, just all of these basic things, which are not maybe useful for themselves, but can help you gain insight into what's going on into the simulation. Things like the open shutter fraction, filter changes, also the internight gaps, and interseason gaps and lengths, and then our normal SRD metrics. And so you see, this is just showing you the metadata metric page, and you can just see that there's a lot of different categories of things that we're looking at here. This is a dense group of metrics. Most of them are just characterizing the physical properties of what's going on. So next, I will talk briefly about the solar system metrics. These again are science metrics. So what happens here is we take a population of solar system objects, we create the observations that those objects would have in a particular simulation, and then we run these series of metrics. So we run this the same metrics, basically almost the same metrics, with different populations, so that we can evaluate how well the simulation is doing for things from the inner solar system all the way to the outer solar system. So the first set of these are discovery metrics, because the very first thing you want to do with solar system objects is discover them. So here we look at like different criteria for discovery. If you had the requirement to have 3 pairs and 15 nights, which is still our baseline requirement for number of observations for a solar system object, or if you improve your software a bit, then you can have 3 pairs in 30 nights. Possibly, if we're very good, we might have be able to do 6 singles and 60 nights. We'll see. There's work ongoing on that, which is why we're measuring it still, but it's definitely a harder problem. And then we just look at, like, out of this population, what fraction could we discover as a function of the size of the objects, depending on what the discovery criteria was. So you come up with things like what's the cumulative completeness or the differential completeness at different H magnitudes. And for the NEOs in particular, we also calculate what that translates to in terms of number of objects that were discovered. So you can see there's quite a variety of in your number of discoveries, depending on what your discovery criteria was. We do the same sort of thing, but look at characterization metrics. So this is how well can we physically characterize the objects. So there's a metric that looks at the likelihood of detecting activity, the possibility for color determination, light curve inversion, so you can get the shape of the solar system object. And for these metrics, the details differ for the inner solar system versus the outer solar system. Currently, we're running all of these metrics for a PHA and NEO population, the main belt asteroids, Jovian Trojans, and TNOs and scattered disk objects. There are other populations we'd like to run as well, but this is what we're running sort of as a standard thing. Or the science metrics. So this is our last category of metrics. This is sort of the place where we're really hoping to increase the number of metrics that we have. And this is when we talk about like, oh, we're missing metrics that are sensitive to a particular kind of science, this is where you'll probably see them show up. So we have categorized these metrics. I know there's overlaps. I know we may have put a particular metric into a particular group, and that might be a different category than somebody else might use. We're, you know, this is how it is for now. So we can move stuff around, but that's generally probably not terrible. We have a set of Srg metrics, which are defined by the LSST science requirements document. So these are overall requirements on the survey itself. Then we have cosmology metrics. And then we have variable and transient science metrics, a group of AGN metrics, a single galaxies metric for at the moment, and some Milky Way metrics. So I'll go through these so that we know what's there, so you can see if there's something that might represent your science or where you might need to add something new. So in the SRD, the sort of highest level metric is these FO metrics. These basically talk about what area is covered to a minimum number of pointings or what median or minimum number of visits you have over a given area. So it's talking about coverage on the sky, basically. In the center here, you see our histogram. So this tells you the area that is covered to at least a given number of visits. These solid lines are sort of the design goals. The design goals are not the minimum goals. So the minimum requirements are 750 visits per pointing. The design goal is 825 visits per pointing. In the design area is 18,000 square degrees. The minimum area is 15,000 square degrees. So some of these numbers you may see looking a little bit lower, that in particular the area, than you might expect. So for example, FO area is the amount of area that is covered to a minimum of 825 visits per pointing. And that's less than these numbers, but it's, if you look at the rest of these numbers, it's all within the goals. And so for example, the FO area, 750 visits is above 18,000 square degrees. And if you look at this plot, you can kind of see why. When you have an area, so this is the number of visits and the area, and so you have this fairly steep cliff here. As you get to as you push the area a little bit bigger, the number of visits per pointing falls off relatively rapidly, and part of that is because of evenness of coverage, part of it is because of edge effects. And so the fact that but it doesn't fall very far, so it's just the area is actually a little bit more unstable than things like the number of visits over the top 18,000 square degrees. So these are our FO metrics. And once you sit with these for a little while, they make a lot of sense. And these are some of the basic things that we need to cover. But it's true that especially the area is a little bit tricky. All right. Next we have metrics on the parallax error. And I noticed there was some conversation about parallax factor coverage and parallax DCR degeneracy. We do have metrics for each of these as well. Currently, we run the parallax error metric for a flat SED and at 2 different magnitudes. And we come up with values over the sky, like looking at this sky map, and then this is the amount of area that has a given parallax error. And so we can categorize these and come up with these values for each simulation. We also calculate the normalized parallax error, which is the comparison of the actual parallax error to what would be the best possible if all visits were 6 months apart, for example. And then we do a similar thing for the proper motion, where we calculate the proper motion error and also the normalized proper motion error, which would be if everything was at the first and last day of the survey, and again at 2 different magnitudes. And then there are some SRD specifications on the visit gaps between number of visits that happen between 40 seconds and 30 minutes, so very quick, rapid revisits. So we have some metrics that look at these as well. For each of these metrics, basically, I'm going to describe them briefly, and then the plots will be sort of the metric sky map, if that's relevant. Then this is the histogram of how much area receives what value. And then if we're calculating summary statistics, I'll pop up the summary statistics here too, most of them. Okay, so now science metrics from outside the project that are contributed generally by the community. We have a series of cosmology metrics. These include a bunch of static science cosmology metrics contributed by DESC. So these are things like what area meets particular depth requirements, once you include dust extinction, and a 3x2 point figure of merit, number of galaxies visible on the footprint, and the median number of visits per pointing. Most of these basically come down to being evaluated on this dust extinction co-added depth in I-band. So you see here, after 10 years, what is the co-added depth with a galactic dust extinction that meets the depth requirements that are set out in the metric. And then these are sort of the summary values that are evaluated from that, as well as the number of galaxies. And then the other part that actually pushed us a little bit on the static science is the transient science in the cosmology group, which is the supernova 1A metric. So here, the metric creates a population of supernova, evaluates, injects their light curves into the visits that are received from at that point in the sky, and evaluates the resulting observations of the supernova against various criteria for discovery and identification. And it counts the number detected and their median redshifts. So you see the number detected over here. So one thing you might notice is that there aren't cuts based on the wide, fast, deep in this metric. There are just an inclusion of galactic dust extinction and what the actual signal to noise of a given visit is. And that's why you can see that there's some objects which would be picked up in the galactic bulge, but generally these areas here are eliminated not because of an a priori cut on what the wide, fast, deep is expected to be, but just because of the fact that they're taking into account the dust extinction and the individual visit limiting magnitude. And we encourage all metrics to include these aspects. Like if dust extinction is important, include dust extinction. If it's not, don't, but definitely include the signal to noise. Then similarly to the supernova 1A, but for a strongly lensed supernova population, there's a similar metric that returns the expected number of strongly lensed supernova to be detected. And again, you can see the same sort of thing here where the depth and the dust extinction are being accounted for. Okay, so those do have some overlap with the variables and transients. Here, I think moving purely into more variables and transients, we have a metric for the kilonova. This injects kilonova light curves into simulated visits at uniform points in the sky. So we have a basic setup that you can customize for your own kind of transient or variable object that generates these light curves and adds as the objects basically at points over the sky. And we can help you set that up if you have a population that you want to evaluate. Could we detect these with the LSST and include things like the signal tones of a given visit? So for the kilonova metric, this actually returns the counts of expected sources using a wide range of detection criteria. So one of the other problems, of course, with a lot of transient or variable populations is that there's like, okay, this is what I could see if I required like this many observations, or these require like multiple filters on the observation. This is what I could see if I just said, I just need to see an observation of it. But you can do both of those and you can return them all with your metric. And we can do things like that. So this is for the kilonova. Similarly, there's a microlensing metric, which injects microlensing light curves with a variety of crossing times. These are now distributed across the sky according to stellar density maps instead of just uniformly, and then says, will we see this light curve amplification? So, we run this with a variety of timescales, partly because it turns out that longer timescale events are very easy to detect. And so if you include them all in the same bin, the easy to detect longer timescales kind of wash out the signal from the short timescale events. So we've worked with the microlensing group to set up these particular bins for timescales, the crossing times. Again, this is very similar. The TDE metric injects light curves from TDEs uniformly across the sky this time and evaluates them with a range of criteria. And then this is a little bit different metric. This is just looking at the time gaps. So the number of visits, the number of gaps that you have between visits that are of a particular time, and it just creates a histogram, but then also what fraction of those gaps are in a particular time range. So these are our metrics that came from a Cadence note about the long gaps. So we're running these for each filter and for all filters for all of the simulations now. And then we have periodic stars. So this is an interesting one. I noticed there was a little discussion of what happens with aliasing for one-day timescales. And it's true, when we run the period detect metric, which basically says, if you put in a sinusoidal light curve of a given period and amplitude, could you detect the resulting variability differently than, could you distinguish it from a uniform light curve? And it turns out that for periods less than 1 day, and we run this for 2 different magnitudes as well. Generally, what we find is that for periods less than 1 day or for periods more than 1 day, it's fairly uniform over the sky. And for brighter objects, we can detect lower amplitude light curves. For fainter objects, we need larger light curves, larger amplitudes. Not that surprising. For periods of 1 day, we notice some non-uniformity and also lower performance in general. But this is where we can take this metric, and then when we have those long gaps simulations, we can see if we see a difference here. For AGN, we have a series of metrics. The AGN collaboration have been is sort of currently updating these metrics. So we have at the moment the number of QSO, which are detected over the sky. Currently just running this in 1 bandpass. It needs an update to run in all bandpasses. We also have a metric that just looks at the time lag, so the gaps between visits and how often we sample the sky compared to a defined interval. So this is essentially counting sampling intervals. And then we have a structure function error metric, which actually takes those time gaps and translates those to an estimate in the error on the structure function that would result. And this is configured to run at particular magnitudes in each bandpass that's just a little bit brighter than the mean individual image depth and includes dust extinction for each visit. So you can see again, the dusty plane sort of falling out naturally from these simulations because of the fact that the dust extinction is and signal to noise of each visit is included. For the galaxies, we just count up the number of galaxies we expect to see across the sky using a luminosity function that has come in through one of the other metrics. For the Milky Way, we do a similar sort of thing where we just count up the number of stars we expect to see across the sky based on the coated depth. We do this with two ways, one including crowding effects and one not including crowding effects. And we've had a lot of discussion about whether the crowding estimates are, in terms of the photometry, are accurate or if they need to be updated. It seems like they're actually pretty good, so that's nice. I know there's some questions and I'm almost done, so we'll include, I'll have to get to those in just a minute. Okay. Then we have one more metric for the Milky Way, which is about brown dwarfs. This is it's actually looking at the volume to which you could detect brown dwarfs with a given parallax signal to noise. So essentially given parallax constant error or relative error. And so we currently run this for the L7 brown dwarfs and sort of estimate what volume on the sky you could probe down to a given parallax signal to noise ratio. Again, you can go to our website to look at what metrics we're running and go through the different groups. And that's probably the best place to look at it. So I think now I will look and see what questions we have, if I can. There we go. Okay.
Thank you, Lynn. We have one question on Slack.
Okay.
From Tima at the very end. I can read it for you if you don't have it handy.
I think, oh, okay, I see. How can we get a metric to be included in this list of science metrics? Oh, yeah, this is actually great. And Timo, I apologize because your particular metric you're asking about is one that we were running currently and we're not running right now, only because I haven't finished updating some of the batch to so some of the pipelines on our end. And we do have more metrics that people are contributing, and we just have a little bit of a backlog to get through there. There's not a huge number. I have a post on community about how to contribute metrics, and we'll be talking about that more. I think Peter has a few slides about it for sure later. Basically, yes, we would love to have more metrics. We just need to know, get the metric into RubenSim. We need to know how to configure the metric. If you just write a notebook showing us what how the metric runs and how you need it configured in terms of the keyword arguments or summary statistics, that's great. For the TDC metric, really the only problem is that because of the way that the summary statistics work, I haven't quite worked out how to make that just fit in, but we will go back and put that in. And then once we get a metric and we understand like what it's useful for and how to configure it, then we will run the metric. Can you, yeah, F0. Sorry. Yes, I should have explained that a little bit more. F0 is a it's a bit of shorthand from the project as well, because it's there's a series of performance metrics which relate to different aspects of the system, and it's not actually F0 is FO, which is F observations, I think, Zeljko. I
Yes. Observing efficiency. How well we can schedule observations.
Yeah. So it's basically telling us about how efficiently we're scheduling the survey and how well we're.
I provided a slide in thread with your plot that describes quantitatively how you do it.
Yeah. So this is basically how we calculate FO. The FO metric is. It really is. It's looking at like what area on the sky we cover with a given number of visits. And then there's different ways to summarize that, because sometimes you care about what the minimum number of visits were, sometimes you care about what the median number of visits were, and sometimes you care about what area was covered to a given number of visits.
There is another question from Aprajita on Slack about your post on community.
That is not the right, that's not the metric post I was thinking of. I'll post the links in Slack when we're done here, because I think that will be an easier way to share that. It basically just, I did make a post about like, here's contributing a metric to RubenSim, and that's what I was thinking of.
I don't see any other questions. Okay, then the plan is as follows. I will stop recording so that we have individual recordings for each of the 4 sessions, but we will stay logged in on Zoom if people want to chat. And then we'll continue in about 15 minutes with the rest of program for today with session 2. So people who want to chat, they can chat without being recorded.